We talked briefly when we began this unit about the Dalton solid sphere model of the atom. And that solid sphere model of the atom, the Dalton model of the atom, said basically, here's the atom. It is a solid sphere like a marble. And each atom is different. Just like you can have different marbles, but in the end, the marble is as small as it gets, or the atom is as small as it gets. And then we went to Thomson, which was the plum pudding model of the atom. The electrons are the tiny little particles, tiny little negative particles. They float around in the sea of positive charge. Didn't know anything about protons or neutrons at that point, but at least we knew about the existence of subatomic particles. Things could be smaller than the atom. The electrons. And then we go to Rutherford. Rutherford and a couple of his assistants working on this experiment in the first part of the 20th century called the gold foil experiment. The gold foil experiment basically looks like this. You got this box. And inside this box is some kind of radioactive material. I'm not sure what radioactive material they used, to be honest, but it doesn't matter. In the end, it produced alpha particles. These particles that have 2 protons and 2 neutrons, they're charged +2, right, because of the 2 protons. Remember, it's not a box of alpha particles. It's a box of radioactive material that will release alpha particles. Now, these alpha particles, they go out the hole in the box, and they go out this way, like this, right? And then they strike a screen. And this screen, or this thin barrier, is made out of gold. Gold's heavy, but it's really, really thin. Talking about, like, you guys, when you cook a turkey in the oven, you put aluminum foil over it, right? Well, we're talking about something like that, except made out of gold instead of aluminum, and thinner. And how many people have ever, how many people take foods class? Anybody take foods? Have you ever used, when you're baking something, gold foil or gold leaf? You guys know what I'm talking about? You can buy gold leaf at the grocery store. Gold leaf is gold. It's real gold. But it's incredibly thin. And because it's incredibly thin, it's incredibly light. And that's why it doesn't cost you $800 to go buy a bottle of gold leaf. Right? Because it's incredibly thin and it's incredibly light. Okay, that's the kind of thickness we're talking about. Really, really, really thin gold foil. Now, Rutherford and his assistants want to observe what happens to these alpha particles as they strike this gold foil, this really, really thin gold foil. So what they do is they set up this screen all around it. We call it a scintillation screen. This scintillation screen will glow whenever these alpha particles strike it. So if the alpha particles hit the screen right here, you get a little bit of a bright spot right there. If they hit the screen right here, a little bit of a bright spot, and so on. We know where the alpha particles hit based on where the screen glows, okay, where the screen scintillates. Now, Rutherford and his assistants made 3 observations with this whole deal when they fired these alpha particles at this gold foil. They found that the vast majority of these alpha particles ended up going straight through. Nothing groundbreaking there or monumental there or even entirely surprising there. Most of the alpha particles went straight through. We'll tell you what each of these observations mean in just a second, but we'll go through the 3 observations first. Most of the alpha particles went straight through. In fact, not just most of them, the vast, vast majority of them went straight through. Now, some of these alpha particles, though, didn't go straight through. Some of these alpha particles, when they hit the gold foil, they changed direction. They deflected. Some of them went like this. Some of them went like this. Some of them went like this. So some of the alpha particles were deflected. Still, the vast majority of them weren't. The vast majority of them went straight through, but some of them, a measurable number certainly, were deflected. And still some more, although less, but a measurable number, bounced back. They were reflected. They bounced back. We'll say a few alpha particles bounced back. Now, where do these three observations lead Rutherford and his assistants, Geiger and Marsden, or his two assistants? You recognize that name Geiger? Where does that come from? Where have you ever heard that name Geiger? Like a Geiger counter, right? Okay. And what's that used to measure? Radioactivity, right? Okay, it's not a surprise necessarily that a guy named Geiger is doing experiments with radioactivity when he's been helping out at least with the Rutherford gold foil experiment, which dealt with radioactive particles, right? So what do these observations lead Rutherford and his assistants to conclude? Well, the first observation, the fact that most of the alpha particles went straight through, led them to conclude something relatively simple. Let me give you an analogy to help you understand this. Okay, we got a football field outside. There's 110 yards on the football field, which for anybody who's listening to this in the United States right now are going to be thinking, what? 110 yards? He doesn't know what he's talking about. 100 yards, right? For us, it's 110 yards, okay? Because we can run farther than Americans can run. And faster. And it's a wider field. My goodness, we got to be way more athletic than the Americans, right? We've got 110 yards. Let's say we've got 110 people at each yard of the football field. And we want those 110 people to run across the football field. But before we send them running across the football field one at a time, we're going to blindfold them so they can't see. Now, we're directing them. So we're kind of directing them, kind of taking them by the shoulders, turning them so that they can go straight across, but we're not going to let them see straight across. We're going to blindfold them before they go, okay? So 110 people, we let them go one at a time. And we find that Aiden, who's the first guy to go, ends up running straight across the football field, makes it to the other side, no problem. Okay, Jazzy, second person to go, runs across the football field, straight across, no problem. Okay. Kelsey, third person to go, runs across the football field, no problem. We find that the vast majority, Bailey runs across the football field, okay, straight across, no problem. Most of the people that went across the football field one at a time ran straight across the football field, no problems whatsoever. Okay, listen, if there was something in the way, they wouldn't have ran right across the football field straight across, right? They couldn't see, they couldn't avoid the people in the middle, they couldn't avoid anybody that was on the football field or any objects that were on the football field. They were blindfolded, they just ran straight across. That tells us that most of the football field has nothing on it. If most of these these alpha particles go straight through the gold foil, it tells us that most of the gold is nothing. Most of the gold is empty space. So we'll say most of the atom in general, not just gold, but any atom, is empty space. "110 people run across the football field, 100 of them run across, straight across, no problem. Then most of the football field is going to be empty space. Most of the atom is going to be empty space in this experiment. But some of them are deflected. All of a sudden, Tyler is running across the football field, and he finds he's really close to center field. Okay, he's really close to the 55, I guess you could call it, yard line. Okay. He's at 53 yards from the end zone, let's say. And we find that as he runs across the football field, all of a sudden, he doesn't go straight across. He makes it to the other side, but his path is deflected. He changes path when he gets to the middle of the football field. And a couple other people do as well. So 100 people went straight across, but 7 people actually changed direction. And all 7 people were relatively close to the middle of the football field. What does that tell us? Well, it tells us that there was something in the middle of the football field that was causing them to change direction. Maybe there's this big linebacker or offensive lineman in the middle of the football field that's pushing people. Okay, as Caitlin's running across the football field, as Cassie's running across the football field, somebody pushes them. Now, they still make it across. They haven't hit anything, but they're changing direction because somebody's pushed them. Listen carefully. what would push an alpha particle out of the way? Okay, we're not stopping an alpha particle here. Okay, the alpha particle is not hitting anything. Right, Liam? What would push an alpha particle out of the way? What would push an alpha particle out of the way? Specifically? Not that specific. A positively charged object, right? So there's got to be something in the middle that's positive. There's got to be a small positive nucleus in the middle. The guy who's on the 5-yard line runs straight across the football field. He's not affected by that linebacker that's in the middle of the football field whatsoever. But Cassidy, who runs across at 53 yards from the end zone, 2 yards from the middle of the football field, is affected by that linebacker. Okay, the linebacker's got a little bit of rage going on. He's pushing everybody that's nearby. He's pushing out of the way. Okay, Cassidy gets deflected. She ends up making it across the football field, but her direction has changed. Now, a few of the alpha particles bounce back. What does that tell us? What does that tell us? Well, let's say that Erica is running across the football field, right in the middle of the football field, right smack at 55 yards from one end zone, 55 yards from the other end zone. She's running across the football field, blindfolded, smiling because this is fun, and then all of a sudden, bam, she bounces back, straight back. Okay, straight back, or maybe she hits the middle at an angle and she bounces back at an angle. But the bottom line is she bounces back. What does that tell us? Well, we already knew there was something small in the middle of the football field. There was something there. We already knew that there was something positive in the middle of the football field. Okay, something small and positive there. The fact that Erica bounced back tells us that what? That small positive thing must be also heavy. The nucleus is heavy, or the nucleus is dense. What does it tell us that? Well, picture this. You got a 2-year-old that's in the middle of the football field. Okay, the 2-year-old maybe pushes Cassidy out of the way a little bit because 2-year-olds like to push. So Cassidy ends up going across the football field but changes direction. Erica's running across the football field. She's blindfolded. She doesn't see what's coming. She hits the 2-year-old. What happens? She knocks the 2-year-old out of the way, and she just keeps going across the football field. It's not somebody that's light in the middle of the football field. If Erica bounces back, then it's something that's heavy or dense in the middle of the football field. So what did Rutherford conclude? He concluded, him and his assistants concluded, that most of the atom is empty space. There is a small positive nucleus in the middle of that atom, and that nucleus has got to be heavy. So Thomson had already discovered the existence of electrons. Now Rutherford discovers the existence of the nucleus, the positive nucleus. Not the existence of protons, but the existence, Jazzy, of a positive nucleus. So here's our nucleus. We're not going to throw out these electrons that Thomson discovered 1897, but rather Rutherford's just going to make them orbit around. You got a small, dense, positively charged nucleus. Most of it's empty space here, you can see. But then you got this electron or electrons that are orbiting around. Does that kind of make sense, guys? Is this our current model of the atom? No, it's not. But it's getting a lot closer, isn't it? Okay, this is, talk about the difference between evolution and revolution. To me, this is revolutionary. This isn't an evolutionary step in our current understanding of the model of the atom. This is revolutionary. Okay? Thomson was revolutionary because Thomson discovered that there was subatomic particles, electrons. But this is also revolutionary because this is a lot more than just a bunch of negatives floating around inside a sea of positive charge. Here's a nucleus. Here's a defined chunk in the middle of this atom, and most of the atom is empty space, which we still, to this day, believe most of the atom is empty space, and there's a small, dense, positively charged nucleus. We just have more to our model of the atom now than Rutherford discovered. Yep. Go ahead.
Wasn't there something about how surprised about as surprised?
Yeah, no, no, absolutely. Yeah, absolutely. This wasn't necessarily something that that Rutherford or his assistants would have predicted, right? They were as surprised as anybody else was at this, right? Rucker made the point of a quote, I think that Rutherford had said at some point after he discovered this, that basically it's like, you fire a shell at a piece of paper and it bounces back, right? That's kind of what like this is like, right? Okay, kind of what this is like, but in the end, it happened. It happened. And that's sometimes how science is going forward, right? Is to say that we're discovering things. Sometimes we have hypotheses, we expect against something, and that's what we get out of it. Sometimes we have hypotheses, and those hypotheses end up being rejected because we find that no, it's not the case. And sometimes we just find something that we're just completely not expecting whatsoever. Yep. Guys, let's take a look at one example here, okay? And then if you have any time left, we'll give you a chance to work on the 3 practice problems you have for homework. So it says, students attempt to determine the nature of an object that's hidden beneath a sheet of plywood by rolling marbles under the plywood. So you're looking at it from above, and then you're looking at it from the side, and you're rolling marbles, and there's something underneath there. Okay, there's a hidden object there. We don't know what it is, but there's something there. We're rolling marbles, and we want to see, based on the path of the marbles, we kind of want to map it underneath it. This exercise would help students appreciate the difficulties encountered by Compton. We talked about Compton, wave-particle duality, the Compton effect, photon momentum, photon energy, right? An electron and a less energetic photon is ejected when an X-ray strikes the... That's not it, right? This has nothing to do with the Compton effect. Einstein and his work with the photoelectric effect, okay, we learned about that. This has nothing to do with the photoelectric effect. Okay, when I had somebody stand up in the middle of the room and we were throwing pieces of paper at the person, okay, that was like the photoelectric effect, right? Energy of the photon, or the frequency of the photon, is what affected the ouches, or the electrons released. Okay, this isn't like that at all. Rutherford and his work on the nucleus of the atom, given that that's what we've just been talking about, that's probably the answer, but can you explain to me why that would be the answer here? If you saw this 2.5 weeks from now, how would you know that was the answer? Yep. Yeah, you're looking at what happens to the marbles to indirectly map what's underneath there. Okay, you don't know what's underneath. You can't see that. But when you look at the marbles that are going right here, going straight through, and the marbles that are going right here, straight through, and the marble right here coming straight back, okay, you're mapping what's underneath it by not actually observing directly what's underneath it. Okay, that's exactly what Rutherford did, right? So it looks like C would be the answer. Let's just double check D to make sure. Thomson and his work on cathode rays. No, okay, this has nothing to do with cathode ray tube, right? Good? No.